Yeah, so this lecture 8 was probably not the most exciting one. We went through a lot of pain doing the bias variance decomposition and stuff like that. So the good news is that we are now almost done with lecture 8. So there's only one last short video, one last thing I wanted to talk about. And these are the different forms of bias we may encounter when we talk about machine learning. So in machine learning, bias is kind of an overloaded term. So overloaded means that the same term is used for referring to different things in different contexts. If you have taken the machine learning 453 class, so statistics 453 that I taught in spring semester on deep neural networks, there we also encountered a bias unit in neural networks. Of course, this one is probably hard to confuse with the statistical bias that we talked about in this lecture. However, in machine learning, there's another type of bias that is often encountered, and this is usually called machine learning bias, or sometimes also inductive bias. And this bias refers to the bias of the machine learning algorithm. You can think of it as the preferences or restrictions of the machine learning algorithm. So it affects different machine learning algorithms differently. A simple example might be a decision tree. If you think of a decision tree algorithm, for example, favors smaller decision trees over larger decision trees. So if there are two decision trees, for example, let's say we have a decision tree like this one, and when we start growing it and we are, let's say, at this point, and this point, or this decision tree, this shorter tree, gets the same performance on the training set, let's say, as this larger decision tree in practice. So the decision tree algorithm would favor a shorter tree because it would stop growing the decision tree if no improvement can be made. So in a certain way, decision tree algorithms favor smaller trees if there are multiple trees that have the same performance, because if there's no improvement in the performance, it would just stop growing the tree. So in that way, decision tree algorithms are biased towards smaller trees. So in other words, if the training data can be classified by a small tree, a larger tree is not considered. So that would be one form of inductive bias affecting a decision tree algorithm. So there is a paper by Dieterich and Kong, 1995. These are the same authors that also worked on the 0-1 loss decomposition paper from 1995 that we talked about in the previous video. And they contrasted the machine learning bias with the statistical bias. So the statistical bias would be referring to the bias and variance that we talked about when we did the squared error loss decomposition and the 0-1 loss decomposition. So here this one refers to the machine learning bias. So let's talk about this one first. So they say a bias can be characterized as appropriate or inappropriate. So there are appropriate and inappropriate biases. So this refers to the absolute bias. I think it was cut off here. It was maybe on the previous page in the PDF. And the inappropriate ones, let's highlight them in red. Red is usually the color that denotes that something bad. So the inappropriate absolute bias does not contain any good approximation to the target function. So these are all the bad cases where the bias is inappropriate, such that the hypothesis space doesn't contain any good solutions. So this would be a case where the algorithm is not very well suited to a given problem. So for example, if we think of image classification, in the case of image classification, I would say a decision tree is really not a good classifier. So in this case, a decision tree would have an inappropriate bias for, let's say, the case of image classification. Now the appropriate one, the appropriate section here, this would be a bias where good approximations are contained. So it's possible, even though there's a bias, it's possible to get a good approximation to the true target function that we want to model. Now there's also the relative bias, which they say can be described as being too strong or too weak. And the bias that is too strong is one that, though it may not rule out good approximation to the target function, prefers other poorer hypotheses instead. So if we have a strong relative bias, again, it is possible to find a good solution in the algorithm's hypothesis space. However, the algorithm may not find it. And another thing here is, if the bias is too weak, the appropriate hypothesis may be found, but the algorithm considers too many hypotheses. So this would be then related to the fact of overfitting. So if we think about decision tree algorithms, if we have a restriction and we talk about a pruned, or let's say a decision tree stump as our algorithm, it has the restriction that it has to be only one level. It's actually arguably a little bit difficult because it could also fall into the inappropriate section, but let's ignore the inappropriate section. Let's say we have a decision tree with a maximum depth of 1. It's not a very deep tree, so in this case we would have a very strong relative bias, which also then will correlate to a high bias in terms of statistical bias, because the algorithm or the model will be too simple to fit the dataset well in most cases, in most datasets, but it will have a low variance. On the other hand, if we have a relatively weak bias, this would be an unpruned decision tree. In this case, we will have a low statistical bias but a high variance, because the decision trees will vary a lot depending on the dataset or on the training dataset, even though the target function is the same as we've seen in previous videos. But anyways, just to briefly show you an example here. So here they ran a simulation on 200 training sets with 200 examples each. And it was a binary classification dataset. So they generated 200 decision tree models. And then they evaluated it on 22,000 test set data points. So in a test set of the size 22,801. And they observed that the mean error rate was 536. 297 of these errors were result to bias and 239 were the result of variance. So that was then computed similar to how we computed the bias and variance in the previous video when we did the bias variance decomposition of the 0-1 loss. On the left hand side they are showing the dataset, or one of the training datasets. On the left hand side you can see it's a little bit small, but you can see these are primarily or only examples from class C0. On the right hand side these are examples from class C1. And it would be easy to fit this dataset perfectly by a diagonal. However, you know that decision trees also have another form of, I would say, inductive bias. So they are not good at drawing diagonals. So decision trees cannot draw diagonal lines. They can only do these staircase approximations. So we get then as the variance something where it's kind of similar here, but then due to the staircase also we have like this these bias errors here. And this is just an example of this simulation study. You don't have to know this for this class at all. I was just pasting this here because I saw that and I thought it might be interesting to some of you to see an application of the bias and variance on a practical problem using this type of simulation study. So if you're interested, I recommend looking at this paper here. Lastly, another case where we would have an appropriate absolute bias, an okay relative bias, which will result in a low statistical bias and a low variance. So this would be a decision tree classifier that can classify a dataset perfectly by just drawing these boundaries perpendicular to these axes. So if such a classifier can classify this dataset perfectly, then this would be a good case with low bias and low variance. Okay, so that was just briefly about the inductive bias. So another very important type of bias that we encounter in practice in machine learning is the fairness bias, the so-called fairness bias. So here, this is a quote from a book. It's saying the term bias is often used to refer to demographic disparities in algorithmic systems that are objectionable for societal reasons. So this means that certain types of demographics are treated unfairly by machine learning models. And what's the reason for that? There can be multiple reasons. Sometimes it's due to the data set. There is an imbalanced data set, but there are also other reasons. So I'm not an expert in this area. However, I highly recommend taking a look at this book, fairmlbook.org. So here you can learn more about the fairness in machine learning and different reasons for the type of bias we may encounter when we do machine learning or create machine learning models, but also suggestions to avoid or minimize this bias. So that also reminded me of a project I worked on approximately 2 years ago, where we developed a system for hiding soft biometric information from face images while still retaining the matching accuracy. So by that I mean we try to hide attributes from face images such as the gender from algorithms. So algorithms were not able anymore to extract the gender of a person from a face image. However, the images were altered in such a way that the face matching utility was still retained. So that means, for example, if you think of an application at an airport where you have a passport scanner, and the passport scanner is scanning the passport and comparing the picture on the passport to the person in front of the camera to see whether it's the same person as on the passport. So this utility was still maintained. However, it was not possible anymore to extract the gender. So in the passport case, that's maybe not so useful, but think of a case, let's say a supermarket or something, where there are cameras to check whether there's, for example, a dangerous person entering the supermarket. So there's still some matching against a certain database. However, the supermarket camera is not able, or algorithms deployed in this camera are not able anymore to extract the gender. So the supermarket owners can't study the demographics of people entering the supermarket. So why is that useful? I mean, it's just like a basic privacy thing, because the people who enter the supermarket maybe didn't agree to have their gender information revealed. So in that way, it would be protecting the privacy of the customers. So in any case, here I looked at the performance of our system, but also on the face matchers we used. So we used different types of face matching algorithms to check whether they still perform well. We also looked at commercial face matching algorithms. So here in this table, this is actually without our system. It's before applying our system. And I looked just at the performance of these face matchers, the commercial face matchers. And I saw, for example, so I looked at people with dark skin color and light skin color. And these tables here show the joint probabilities. So what is the proportion of female predicted as female? That would be 42.4%, and male predicted as male is 54.8%, and so forth. So the probability of making a wrong prediction given that someone is male is about 2.8%, and the misprediction of predicting someone wrong, the gender wrong if someone is female, is 2.9%. So this was actually for the binary gender classifier that they implemented in the commercial software. So they had a binary gender classifier they implemented. This was not for the face matching here. So this was for people with a darker skin color. For people with a lighter skin color, you can, for example, see that the probability for making a wrong prediction was 3.2% for male people, and for females 1.4%. So what you can see is, so for people with a darker skin color, if you look at both male and female, so the total number of mispredictions. So the total number of mispredictions here is actually higher, the probability of misprediction, than for lighter skin color. So in that case, the system is slightly biased towards performing well on people with a lighter skin color. However, it doesn't really perform very well on people who are white and male. So it was one bias in this certain system here. So in an ideal world, the error rate would be equal for all cases here. Yeah, just briefly, we had multiple follow-up papers here in the next couple of years where we tried to also balance this out for our system. So again, in the previous slide, I showed you a commercial algorithm that we evaluated. So we didn't have access to this algorithm. We don't know how it was trained and so forth. When we trained our algorithm, we tried to minimize biases by a simple technique of oversampling. So there are different types of techniques to minimize bias. Here we designed better phase prototypes, and we also did oversampling. But yeah, that goes maybe into too much detail here. I just wanted to highlight that there could be issues if you are not careful how your classifiers perform on different demographics. So it's also just important to keep that in mind when you design machine learning systems. Yeah, and lastly, another paper that was just recently accepted for publication this week. So it's not published, but it's available on arXiv. It will be published in the next couple of weeks. So here we also considered different data sets. So there was, for example, the Morph2 dataset, which consists mainly of people with a darker skin color. There is the Asian face dataset collected by New et al., which consists mostly of people from Asia. And then the KACD dataset, it contains people from various different regions and backgrounds, but I think it's more biased towards white people, for example. And here we also considered different data sets when we evaluated our system. In an ideal world, so this was more for benchmark reasons, just comparing the performance of our method on different data sets. But if you would employ a system like that, you would maybe also consider combining these data sets. But again, balancing out data sets, it's not the only thing to consider when designing fair systems. And yeah, I recommend really looking at this book here as an additional study exercise. So beyond the lectures here, to also read some chapters in this book, because yeah, this is also an important topic in practice. Okay, so this is it for lecture 8, and in the next lecture, in lecture 9, we will take a look at more simpler topics of model evaluation. So basically how we evaluate machine learning algorithms fairly in practice, and for example also how we create confidence intervals for our accuracy or prediction error.